All right, in this video we're going to be doing some linear algebra practice problems about orthogonal spaces and orthogonal complements, and I thought there was something else, but maybe that's just it. W is a subspace of R5 spanned by A, B, and C. What's the dimension of W perp, the orthogonal complement to W? Justify my answer. Okay, one thing that we know from the lesson is that the dimension of the complement is going to complete the subspace, or complete the space that you're living in. So the dimension of W plus the dimension of W perp is going to be 5 because it lives in R5. Okay, so really our job now is to determine what is going to be the dimension of W. And W is the span of A, B, and C. So we're going to see what's the dimension of that span. How many independent vectors are there? I know it's at least 2 because I don't see any vectors that are proportional to each other, but I guess it's possible that, C is some combination of A and B. So I'm going to grab a calculator and type in A, and I don't know if that's actually big enough. Matrix Desmos is a little weird. The keyboard's a little large for my taste. I want to be able to show you what's going on up here more so than what's going on down here, but whatever. Okay, so I've got A here. I'm going to call for a reduced to echelon form of A. I'm going to count, there's only 2 pivots. I think you can see that, even if it's pretty small. There's only 2 pivots, so that means there's only 2 independent columns. I can write the third one as a combination of the first 2. What this is telling me is 2 of the first minus 3 of the second equals the third. And I think that's pretty believable if you look at A, B, and C. So with that, I know that the rank of A is 2, or that the dimension of W is 2. So I'm going to say dimension of W equals 2. Therefore, the dimension of W perp is going to be 3. All right, the next one, W is the subspace of R4 spanned by X and Y. Write a non-zero element of W perp. Okay, so we just know that that's going to be some vector V. And if it's in the orthogonal complement to W, that means it's orthogonal to every vector in W. And that's going to be specifically X and Y. Okay, so V dotted with X needs to equal 0. And V dotted with Y needs to equal 0. Yeah, I think I'm just going to write V as A, B, C, and D. Okay, so I know that from V dotted with X, that's going to be A plus B plus C minus D equals 0. And Y dotted with V is going to be no A's, 1B, negative 2 C's, plus D equaling 0. Okay, this is a linear system of equations. I can solve this with some row reduction. I'm sure there might be a faster way to do this, but I'm going to subtract the second row from the first. Row 1 minus row 2. Yeah. All right, so as long as A equals negative 3C plus 2D and B equals 2C minus D, I'll be fine. So I can just let C and D, both be 1 if I want. Or I could make one of them 1 and the other one 0. Or I could do something, totally crazy if I wanted. But I'm just going to say V is going to be where C and D are both 1. So A is negative 3 plus 2 is negative 1. B is 2 minus 1. C and D are both 1, and there you go. That will work. I'm just going to quickly check. Yeah, against X, that works. And then 0, 1, 2, negative 2. Yep, it's great. Okay, that's a non-zero element of W perp. All right, W is going to be a subspace of R5. Okay, I'll set of all points. U, V, W, X, and Y with U plus V equals W and 2X equals 3Y. Okay, so there's kind of 2 equations. Basis for W perp. Okay, so I think I'm going to start by writing a basis for W and then just use the recipe that we talked about in class. Okay, so I'm going to have W and X are kind of my dependent variables. So U, V, and Y are my independent variables. Okay, so U, V, and Y. Okay, W is U plus V, X is 1.5 Y, and Y is 1. Right, then I'm going to say, all right, I'm going to write a basis for this. All right, so U is going to be 1, 0, 1, 0, 0. V 0, 1, 1, 0, 0, and then for Y 0, 0, 0, 1.5, 1. Okay, now at this point, once you've got a basis for the original space and you want to write a basis for the orthogonal complement, you're just going to kind of be using fundamental theorem of linear algebra, the orthogonality of the 4 key subspaces. And you can either write these basis vectors as rows and find the null space of that matrix, because the row space and the null space of a matrix are orthogonal, or you can put these into columns and find the left null space, but that involves transposing, writing them as rows, and then finding the null space of that. So I'm just going to start by writing them as rows. Let's start with 1, 0, 1, 0, 0. Okay, and I'm needing to find the null space of this matrix. All right, so I've got just thinking about this. I'm going to just solve this equation for x4, right? And just make x5 the independent variable. So that would make x4 negative 2/3 of x5. Yeah. All right, and then x5 is an independent variable. All right, so a basis for W perp, okay, W perp is the null space of this matrix in blue here. That would be for x3, negative 1, negative 1, 1, 0, 0. And for x5, 0, 0, 0, negative 2/3, 1. Okay, now we're wanting to write a basis for W perp, and W is the column space of the matrix A. Okay, so I need to use what we know. And so what we know is that the column space of A is going to be orthogonal to the left null space. So that would be the null space of the transpose. Okay, so I'm just going to transpose the matrix and find its null space. Okay, so I'm going to add the first row to the second row. And I don't know, I froze up on that. Okay, I added the first row to the second row, and I was just thinking about what's going to happen after. Now I'm going to subtract the second row back from the first, and I'm going to have a 0 and a negative 2. and so that means x1 equals positive 2, x3, x2 equals negative 3 of x3, and x3 can be whatever it wants. Okay, so a basis for W perp in this case would be 2, negative 3, 1. This one's pretty similar to the last one, but we're just going to start off thinking about W is the null space of this matrix, and we want a basis for the orthogonal complement. And what we know already is that the null space of B is orthogonal to the row space of B. So what we're going to need to do is find the row space of B. And one way to find a basis for the row space of B is to report the columns of the rows of the reduced row echelon form of B. And when you know B is already in reduced row echelon form, so I'm going to say that the basis is going to be 1, 0, negative 2. And also 0, 1, negative 1. Maybe you see here what I was saying, a couple weeks ago about how, vectors are kind of just vectors. And, we got these vectors because they were the rows of B. But if we think about a basis for the orthogonal complement of W, which is, vectors that are orthogonal to the null space vectors, we're looking for vectors that have 3 components in them, right? And whether we write them as a row or as a column, it's, we're going to be dotting them and seeing if they equal 0 if we're trying to really find if they're orthogonal. So really, you write them as a row, you write them as a column, it really doesn't matter. Number 6 is asking us to write a basis for the orthogonal complement to the row space of the matrix C. Okay, so what we know about that is that row space is orthogonal to null space. And then, looking at matrix C, I can tell that it's non-singular just looking at it. It's got 3 pivots. I could reduce it to the identity matrix. It's upper triangular with all non-zeros along the main diagonal. However you want to describe this. It's got a non-zero determinant. It's non-singular. So I can say, well, if it's non-singular, that means that its null space is just the 0 vector. Right? So, but then if it's just the 0 vector, then that's going to be the basis for the null space, which is the orthogonal complement. So I'll just say that's the basis for W perp. Now number 7 is saying that W is the row space of the 4x6 matrix N. And the dimension of W perp is 2. What is the rank of N? All right, well, I think first we should think about W is the row space of a 4x6 matrix N. That means that W is going to be in R6. And I know that because that 4x6 means there are 6 columns, meaning the rows are 6 entries long. And so I'm going to start off thinking, okay, W is a subspace of R6. And the dimension of W perp is 2. That I can figure that means the dimension of W is 4. And we want to know what's the rank of N. Okay, so that's going to be the dimension of the row space. So that's going to be the 4. How I might explain that is, a few steps away, is that, okay, W is the row space, and we said that the dimension of W is 4. So we know what the dimension of the row space of N is. And we also know that the dimension of the row space and the column space of any matrix are going to be equal, right? Because rank is invariant under transpose. And the dimension of the column space, that's the definition of rank. That's what we're saying. So the rank of N is going to be equal to 4. Now the last one we've got for you is W is the column space of 7x5 matrix P. And the dimension of the orthogonal complement of W is 3. What's the nullity of N? Okay. So I think I'm going to say, all right, well, if W is the column space of P, then W is going to live in R7 because there's 7 rows, meaning the columns are 7 entries tall. So let's say, okay, W lives in R7. And the dimension of W perp is 3, so that means that the dimension of W is 7 minus 3, which is 4. And that would be, okay, so that means that the rank of P is 4, because W is the column space, the dimension of the column space. That's equal to the rank of P, which is now equal to 4. And we know that the nullity of P is going to be equal to the number of columns of P minus the rank of P, which is going to be 1. All right, and so that's all I got for you for this problem set. I'm not sure if I'm going to be able to stitch this video back to the other one. Who knows, I might be posting this as 2 videos. I accidentally clicked a wrong button when I was in the middle of recording one of the problems, and so I had to make it in 2 videos. So that's all going to be all for this video. Thanks for watching.